Here in 9E.2, we're going to be talking about still trigonometric parameterisation, but rather than moving in a circle, we're going to have ellipses. Okay, so it's sort of an elongated circle. And so we've got the function. The only significant difference is the amplitude of the x component and the amplitude of the y component. They're going to be different, and that's going to dictate the boundary of the ellipsoid. Got a description of it there for you. Okay, so we've got, consider a footballer running laps. He's fit and healthy. It takes him 60 seconds, we'll tell him a bit later, to run a lap. His position is given by, so I'll write up the equation, x of t is 85 cos wt, and y of t is 70 sine wt. And so if you sketch that on the Cartesian plane, you get pretty well a footy oval. I did some research into this. There's a bit of variance, but we have 80 metres, about 150 metres, 160 metres long, and then 140 metres across the guts. So there we go, that's the equation. Part A, show that the Cartesian equation of the footballer is this one. We've got x squared plus x squared on 85 plus y squared on 7. Well, what we're going to start with, right, is we're going to start with, we'll start with these equations. And we can rearrange them such that we have x of t on 85 equals cos of t. And we can do the same for sine. Right? Y of t on 70 is equal to sine of wt. Alright, just dividing both sides by the coefficient out the front. Alright, and then what we'll do is we're going to make this statement that cos of wt or sine of wt squared is 1. Alright, and then we've just got a simple substitution. Well, cos of wt is this one. It's x on 85 squared, and sine of wt is y on 70 squared. And so that's the substitution, that's the rearrangement, that's how we're getting to the Cartesian equation of the ellipsoid. Okay, next part, the footballer takes 60 seconds to run a whole lap, so to run the whole way around. Determine the value of w. So we're not told this component, but it maintains from the previous part that the period of the time it takes for one whole lap is 2 pi divided by w. So we have 60 seconds is 2 pi on w, and so we'll rearrange and get w is pi on 30. Alright, so we've determined the value of w. And then part C, find the position, the velocity and the speed of the footballer after 20 seconds. So I haven't really given you enough room there, but we should be able to squeeze it in, I think. So firstly, the position, we're just going to be substituting t is 20 into this equation. Alright, so we're going to have 80 cos, now w is pi on 30 times 20, and 70
80
sine pi on 30 times 20. Alright, so that's it when we perform the substitution. And pi on 30 times 20 is 2 pi on 3. Alright, so it does simplify. So we have cos of 2 pi on 3. I'm going to write these here because we're going to do a video.
Mr. Rose, I think it should be 85.
85,
Yeah.
thank you. 85. Yeah, cos of 2 pi on 3 is going to be minus half, and sine of 2 pi on 3 is root 3 on 2. So they're what we're going to be substituting in here. And so its position, 85 times minus half. So what's that? Minus 85 on 2. And sine 70 root 3 on 2. Maybe simplified a little bit. You could express it as a decimal if you wanted to, but that's its position. Okay, next we need the velocity and the speed. Well, we know the velocity vector, right? The velocity vector is x dash of t and y dash of t. So let's come up with the velocity vector, and then we're going to put the t value, t is 20 seconds, into the velocity vector. So when we differentiate it, we're going to get 85 minus 85 pi on 30. Let's go to your negative sine of pi on 30 minus t. And we'll have 70 pi on 30 sine of pi on 30 t. Alright, so that'll be the velocity vector. And we're interested when time is 20. Alright, so we're going to perform the same substitution again. We have sine of 2 pi on 3, because when we substitute time is 20, we're going to have the 2 pi on 3 there. So therefore, when t is 2 pi on time is 20, we're going to have the velocity is, and what are we going to have here? We're going to have minus 85 pi on 30, and that is sine of root 3 on 2. Here, 70 pi on 30, and minus half. Alright, and it can be simplified a little bit. We'll have at the top minus 85 root 3 pi on top of that should be 30 up to 60 minus 75 on 60. Okay, so that's the velocity vector, and you could express them as some decimals if you wanted to. That's showing how fast it's moving with regards to each component, both the horizontal and the vertical. Okay, and lastly, the speed. All right, well, the speed is just the magnitude of velocity, isn't it? So the speed, we'll write out the formula here. Got us the square root of x dash of t squared plus y dash of t squared. All right, so that's the formula for it. And we want the speed at this location, so we're going to do the magnitude there. So that's going to be the square root of 85 root 3 pi on 60 squared. All right, and I evaluated it before, 8.5 meters per second. Now the difference between these two, right, is between the ellipse and the circle is on the circle, it's going to move with a constant speed. The speed's going to be the same. Whereas with an ellipse, it's going to move faster in a certain location. I won't justify where just yet, but it's going to move faster at certain points and slower at others. So, you know, you're picking up your pace and it's slowing down at certain points. And you're going to solve that in the exercise. That'll come up. Okay, so let's get into it. Yeah, E2.